Right, so there's some issues to do with autocoding. If I go back to the myths, some of the comments I make here will not be specific to autocoding, but they're quite important in a way. So we can as processes get faster, we can accommodate poor efficiency in code. Well, that just encourages bloat, to be honest. If you think about the way in which processes have speeded up over the past 20 years, does a PC running Microsoft Word run 100 times faster than it did 20 years ago? No, it certainly doesn't. In my own domain, when I first started working with real-time embedded systems, the interrupt rate was probably a millisecond, between interrupts. Am I really saying that with processors now 1,000 times faster than I started, I would even contemplate handling rates of a microsecond per interrupt? Absolutely not. It's just not sensible. So that doesn't follow. The thing that you find you actually are getting now, you're not getting actually faster and faster processors, you're getting the performance delivered in a different way. So you're getting multi-core processors. If they just try to increase the clock speed internally, all you'll get is a massive heating effect. And we can't actually, in embedded missile systems, we certainly can't afford massive power dissipation. So you now get multiple cores, which means you've got to get parallelism. Without parallelism, you get nothing from multiple cores. Now, do these tools actually support parallelism? That's a good question. If you want to support parallelism, you've got to understand the granularity of your platform, and you've got to understand how you balance a load across the platform. So you've got to understand the execution behavior of that code as well as what you're going to run it on. And that's certainly something no automatic tooling system provides at the minute. It's very difficult to do in any case. Even if you don't use automatic tools, it's still a very difficult thing to do. But it's not an easy thing. Certainly in the automated environment is not at all easy. And of course, things are only going to get worse because the number of cores is going to grow. At the minute, we have 2, 4, 6, maybe 8 cores as a possibility. In the future, we're going to go to tens, possibly hundreds of cores when we start talking about general purpose graphics processors. It will get harder, and you'll have to get the granularity in these tools so that you can exploit this. If you don't exploit it, you're getting no payback at all. The processing power is not going up in reality, it's staying still, or even coming down. More functional products because of faster processors. Go back to the Word analogy. So we've got faster processors. Has Word had any more functions added to it over the last 10 years? Absolutely not. It's just presented differently. So we've not got better. We've not got anything better. I think a lot of people would think it's worse than it used to be because it doesn't look the same as it used to. That's not really the issue. The issue is that it doesn't mean you get better products. If you want to get better products, you've got to exploit the multi-core issues. That's, again, the same problem as before. It's difficult. So we might introduce more accuracy and complexity into the solution. Well, complexity for its own sake is not really worth doing. Accuracy, maybe we do gain something with higher precision floating point. But actually, if you're in a closed-loop control system where you've got 12 to 16 bits of input data, validity of input data, going to a 48-bit floating point number, or floating point value, what's it gain you? Not a lot. It's completely unnecessary. And there are other areas where historically engineers would have optimized things. They'd have looked at algorithms where they could use small angle approximations. In autocoding, they'll use full accuracy sine and cosine. Things like squaring numbers would have been simply done by multiplying 2 numbers together. In autocoding, it will be a power function, making it far more complicated than it needs to be, consuming the extra processing power, and so thereby not giving us the gain we should be able to get. Added to that, the generated code is quite complex structurally for most autocoders. We're adding complexity. So I've actually seen cases where auto-coded or auto-generated code can defeat the compiler's optimizers. So you end up with code that you think is a bit bigger than it should have been, but actually the effect is far, far worse because the optimizer has been completely defeated. It's actually interesting to look at static complexity metrics for these bits of auto-generated code. If they show it's very complex, you can pretty much bet that the compilations phase is not going to do as good a job on it as you might have expected. Right, autocoding shortens product development times. So how long does coding actually take? 5, 10, maybe 20% of the time. So you reduce that, but it's only one part of the task. Does it help anywhere else, having autocoding? Well, it will eliminate low-level unit tests because there's no units to test anymore. At system design level, I think it depends on the tools. I think probably there are some helps there, but I think they're incredibly difficult to quantify. So if you think about V&V, what we've done is with autocoders, we move all the testing to a higher level. And that follows all the faults are found at that high level of integration, which means that we're now in the area where they're traditionally more expensive to fix. So have we saved anything? It's hard to justify saying you've saved anything at that point. And the lack of low-level transparency makes it very difficult to actually understand how you can improve the test coverage to get complete coverage of your application if you can't understand why that code is there relative to the original model and how to actually provoke test cases or to generate test cases that actually exercise those bits of code. It's very difficult unless you've got the transparency and understand how the model is being translated into the final code. So it's not saving anything there. And a final problem is where you are testing, even at the highest level, you make a small change to the model. It doesn't necessarily mean there's going to be a small change to the code. You actually might get a very, very significant change to the code, which means you can't localize retesting, which is what you'd ideally want to do. So it's hard to say whether it does actually save us anything or not. Sorry. So how can we overcome these apparent shortcomings? Well, it's obvious, really. We just take control of how the code is generated. If only it was that easy. What we need is open code generation strategy. So the end user has complete control over the code that is generated. And the code then is generated for the product domain that is appropriate, not trying to generate a generalized solution. So the MDA, PIM, BSM approach, with the end user having control over the translation technology is an obvious way to solve this. It seems like the sensible way to go, really. We can use the translator can effectively capture the product domain knowledge and then provide code that is suitable in all respects for that final product. We can capture functional and non-functional concerns, and what we're effectively building is an architecture method model. For this domain and this kind of application, this is what we want the application to look like, and these are the rules we'll use to translate these structures in the model into these elements into code. This is certainly feasible. I'm not convinced it's common, and I don't think it's necessarily trivial to capture all this information, but if you can do it and you can use it repeatedly, you should get a saving.